Okay, we are looking at this family of second-order differential equations corresponding to a forced harmonic oscillator where the forcing function is cosine of omega t. Now, in the first video, we were able to solve that. So we got that the solution to the associated homogeneous equation was just a linear combination of cosine of 4t and sine of 4t. A particular solution was 1 over 16 minus omega squared times cosine of omega t. So not surprising that our particular solution was a multiple of that forcing function. Then in the second video, we went and we looked at Desmos, and I entered in this family of curves, and we played around a little bit with the different possible values that we could have, a little for K1 and K2, but mostly for omega. And what we saw was that when omega, which is the angular frequency of the forced response, was close to 4, which is the angular frequency of the natural response, or the solution to the associated homogeneous equation, we got a curve that looked something like this. What's happening here is that these guys, because I can rewrite this as just a single cosine function of 4t, just a transformation of cosine of 4t. So this trig function and this trig function are pretty close to each other. They're both kind of close to just being some transformation of cosine of 4t. So there's going to be a time when they're really in sync, when they're hitting their high points at just about the same time. That's going to be when they're really reinforcing each other, and then they hit their low points at about the same time as well, and so they're reinforcing each other there. Then they fall out of sync for a while. So then we're going to start to have that they're canceling each other out, and so the overall solutions are going to shrink in their value. Then they get back in sync, so they reinforce each other, then they get out of sync. And when we have that phenomenon, we call that beating. And so what we're trying to do is see how an equation that looks like that could lead to a graph that looks like that. Okay. And I'm following the book here. I'm not going to do a full-on proof that this exactly works every single time. I'm going to suggest by looking at a particularly nice example. So what I'm going to do is I'm going to choose a very nice initial condition, which will give me super nice values for K1 and K2. And we're going to take a look at the function that we get in that case. Okay. So I'm going to suppose that my initial condition is that y of 0 is equal to 0, and y prime of 0 is also equal to 0. That is not necessary for us to have beating. I wrote it over here, so I would have room to work. Okay, I'm going to calculate what y prime is here. Y prime would be 4k1, negative 4k1 times sine of 4t, plus 4k2 times cosine of 4t, minus 1 over 16 minus omega squared times sine of omega t, and there's an extra omega in here. Sorry, because I'm using chain rule. So when I take the derivative of cosine omega t, I get negative sine omega t times the omega. Okay, now if I plug in 0, I'm supposed to get out 0 for that. But if I plug in 0 here, this piece is 0 anyway. So I get 0 plus 4k2 times cosine of 0, which is just 1, minus 0. Oh, that's nice. Okay, so K2 must be 0. So we're able to kill off that term. Okay. Now, if y is also 0 at time 0, okay, then I'm getting 0 when I plug in 0 to this original function. I'm just not going to bother to plug into this term because we're going to have K2 being 0. So 0 would equal K1 copies of, I know that cosine of 0 is just 1, so this is just K1, plus 1 over 16 minus omega squared times cosine of 0, which would be 1. So that tells me that K1 is negative 1 over 16 minus omega squared. Okay. That's kind of nice. So for this particular initial condition, I can rewrite my solution as just y is equal to negative 1 over 16 minus omega squared times cosine of 4t, plus this piece drops out because our k2 is 0, 1 over 16 minus omega squared cosine omega t. And I think I'm just going to factor out a 1 over 16 minus omega squared. And then I can just say I'm getting cosine omega t minus cosine of 4t. Just choosing to put the positive term first and then subtract the one that had a negative sign in front of it. Okay. So that's the solution that we're going to be taking a look at. Okay. All right. Now it turns out all solution curves will have similar behavior, but this one it's just easier to see a little bit how it's reasonable that I'm going to get something that looks like that, because that seems just a little bit crazy. Okay. All right. So let's just notice that this would be the real part. So if I had y tilde equaling 1 over 16 minus omega squared, e to the I omega t minus e to the I times 4t, this would just be the real part, because the real part of this would be cosine of omega t, and the real part of this would be cosine of 4t. Okay, so I can say that my y is just the real part of this y tilde, which is kind of cool. So now we're going to explore what does this thing actually look like. And I'm going to introduce two new numbers here. So I'm going to introduce alpha, which is going to be 4 plus omega over 2. That is the average of the angular frequency of the forced response and the angular frequency of the natural response. Okay. Now, I can do that. I can let alpha be whatever I want it to be. Why I want to do that is not immediately clear. It turns out that's going to be helpful. Okay. So your job isn't to say, why did she think to do that? What on earth is going on? Honestly, the reason I thought to do that is because I read the book and that's what they did. And I said, that was very clever. I'll put that in a video. Then I can look clever too. Okay? But I didn't come up with this on my own. This is just, it's going to be helpful for rewriting this in a way that suggests why that beating behavior that we know we're going to get, because we entered this into Desmos, at least we know we'll get it when omega is close to 4, that beating behavior does fall out of things. Okay. So then I'm going to define beta to be omega minus 4 over 2. So it's half of the difference between the angular frequency of the forced response and the angular frequency of the natural response. Again, why am I doing that? Well, because they did it in the book and it made things really nice. Okay. So it just turns out that this is going to give us a useful way of describing things. Okay. Now, I'm going to basically take this and I'm going to try to rewrite this. Right now it's written in terms of omega and 4. What I'd like to do is rewrite this part in terms of alpha and beta. So I'm going to just note that alpha plus beta, well, that would be 4 plus omega over 2 plus omega minus 4 over 2. Well, that's 2 omega over 2. That would be omega. So I could rewrite omega as alpha plus beta. This is very exciting. If I take a look at alpha minus beta, that's going to be 4 plus omega over 2 minus omega minus 4 over 2. Now when I distribute the negative, that becomes plus 4, so that becomes 8 over 2, which is just 4. So I could rewrite this 4 as alpha minus beta. Your job right now is not to understand why I want to do that, but merely to see that, yes, that could be done. Okay, so y tilde, my complex solution that the real solution that I have is just the real part of, yes, okay, is 1 over 16 minus omega squared times e to the I times alpha plus beta times t minus e to the I times alpha minus beta times t. Okay, so I'm going to just rewrite this one or two more times. So let me keep that line up. Okay. All I'm going to do is multiply things out here a little bit. So I'm going to say y tilde is 1 over 16 minus omega squared times. This would be e to the I times alpha t times e to the I times beta t. Because of course if I distribute the I and the t, I just get I alpha t plus I beta t. But when I'm adding the exponents, that just corresponds to multiplication. Okay. Minus, I can basically do the same thing here. I'm going to get e to the I alpha t, e to the negative I beta t, like so. Okay, so that is a way that I can rewrite my complex solution. You might notice there's an e to the I alpha t in both of those terms, which we'll be able to factor out, and we'll do that in just a moment. That'll be where we pick up in the next video.